Hey everyone, and welcome back to the real data science live stream, and welcome back on YouTube, and welcome back, welcome in the studio, Ismail Aydin. This is a real data science meetup, and you'll see that in the meantime, people are gathering in this room. We are streaming from our Utrecht office today. And many people ask, why do you put all this effort? Why do you conduct those sessions? And the reason is we think that real data science has been built on the shoulders of giants. The open source community is thriving, is giving the pulse to what's happening in the data science world. And this is our way of giving back to the community, by sometimes intriguing, sometimes really difficult, sometimes really hard subjects that we want to record and want to show you and talk to you about. Today we are joined by Ismail. Ismail, welcome.
Good to be here.
Yeah, thank you. How long have you been with PA Consulting?
A little over 4 years. It's about 4.5 years now.
4.5 years. And what kind of projects do you do?
All kinds of projects, actually. The nice thing about data science is that it's a very varied type of work that we do, which really touch bases all kinds of topics within the grand scheme, the grand field of data science.
Yeah.
But me in particular, if we look at the past few years, the types of work that I did, it kind of changed between IoT, machine learning, especially machine learning, like building models, and that's really what I do. So it's really about building predictive models
Cool.
for companies.
Yeah.
Yeah.
Cool. Hey, and then survival analysis.
Yeah.
That's a topic you don't hear often
No, that's true.
come in the media.
So
And we'll hear more about what it is.
Yeah.
But why did you think of survival analysis?
Well, that's an interesting topic because exactly as you just mentioned, it's not something that you hear that often. So I wanted to give a session this time about a topic that's a bit unfamiliar within the data science community.
Yeah.
Just to make it unique and
Yeah.
also very fun.
Yeah.
Because I think, because it's unique, I think it will catch a lot of interest of people.
Excellent.
Yeah.
Yeah. Hey, and you have experience with, where have you applied it?
To some extent, I have building it mostly on my free time on models. So there was this interesting case in where actually you can find it on the internet as well, where you have data of hard drives.
Yeah.
There's this company that produces hard drives, and they made their data of the performance of hard drives publicly available.
Yeah.
If I recall, I think it's 50 gigabytes of data they have of millions of hard drives that were installed on PCs over time. And they have this condition of the hard drives all logged, so you can just download it and just build a model that tries to predict why a hard drive will fill.
Excellent.
The company did that itself as well, actually, to improve the quality of their products. So,
cool. Excellent. That sounds like a cool example.
yeah.
All right. So, as any of those presentations, it's going to be mathy, in depth, and I know Ismail long enough to know that we are good on that side. Flick forward if you can't follow, or just replay it. With all having said that, Ismail, I want to ask you to give it a go. Give it a go and show us what you have.
Yeah, thank you. All right, well, as you all know, today's session will be about survival analysis. So what is that exactly? To make it simple, survival analysis is essentially all about trying to predict a time to an event. And it doesn't matter what kind of event that is. It can be an event of a person dying, it can be an event of a machine breaking down, or a hard drive breaking down. Which is actually the main reason why survival analysis mostly have been used in the medical field, especially in toxicology, in drug treatment, and patient treatment. But for today's session, we will use predictive maintenance as a case for survival analysis. So, the whole idea around predictive maintenance is about figuring out when a maintenance should be performed. That's one thing, but the second thing is, of course, not only fixing the problem, but understanding why the problem occurred in the first place. So when you start to do maintenance, it's not always good to start to do maintenance in the beginning. It's all about finding the sweet spot, that the moment when you can afford doing the maintenance, but not, for example, if you need to replace a machine, you don't want to discard that machine too quickly because it's quite expensive. You want to find the right sweet spot when it has been operated long enough. When you discard it, it doesn't, for example, cost too much money for the organization to make that change. To give a really practical example, if we take an engine of a car, you can first off do oil analysis, and based on oil analysis get a feeling of what the performance of the engine is, whether it's in good condition or in bad condition. But over time, you can get a lot of extra features that will give you a better impression of what is really happening. So for example, when the engine starts to vibrate, it becomes a more important indicator of whether the engine will break or not. And over time, you can also use thermal images to see like areas where things heat locally very much or not. And when that gradually builds up, at some point, you will get smoke, and then your engine will die out. Yeah. So it's really all about using these indicators to get a feeling of what you think of that its survival over time will look like, and then select the sweet spot of when that exact right moment is. For example, when you suddenly know, when you can predict that there's a sudden drop in its survival rate, then that should be like a little bit before that moment should be the time to perform that maintenance, either by performing the maintenance or just by changing the engine. So, as a data scientist, we always work with data. So what is the typical data characteristics when you work with survival analysis? Which is actually quite challenging, because in predictive maintenance, you have multiple units. So imagine you have 10 machines. Now, every machine is unique. So if you want to build a model, then you have to deal with situations like, okay, am I going to build a model that predicts the condition of all 10 machines, or am I going to build a model for every unit individually? So that is one challenge, when every unit can have different types of data. Engines are always something that is continuously operating, so you get dynamic data, but in most cases it's easier to work with static data. So you also need to be able to make that transition between dynamic data, static data to make it workable. You always work with a lot of historical data. However, because of the natures of machines, you can always have problems with the historical data of machines that you have. So for example, if you buy a second-hand car, you have an engine that has been operated to some point, but you have no idea how that machine performed before you bought it. So these are typical issues that you have to face with when you build survival model. But we get to that in a few slides later. Relevant features. How do you know which features are relevant, which features are not relevant, which features have a high enough indicative power on what the survival of that engine over time will be and which one not? You don't always have labeled data. I can give you an example of a colleague of mine who worked actually on building a survival predictive maintenance model. They had data of 15 years of the machine, and in those 15 years, it only had one failure. So how are you going to build a survival model based on that? So these are the typical issues and challenges that you face with when working on survival analysis, which only adds complexity to the problems. But that's our sweet spot. We love complexity. So when it comes to survival analysis, or at least predictive maintenance, there are different types of questions that we can ask and different types of answers that we can give. And based on the question, the type of methodology that we use and techniques that we use differ. For example, in predictive maintenance, if your question is how many days or cycles are left until the equipment fails, you build a typical regression machine learning problem. So that's not survival analysis, it's just machine learning. If your question is, will the equipment fail within the next month, yes or no, it's then a classification problem, then again, it's just simple machine learning. Yeah, simple, it's machine learning. However, and this is where it becomes interesting, if your question is, how does the probability of failure change over time? You cannot build the typical regression or classification problems that we know. That is exactly survival analysis, trying to fit a curve that tells you what the survival rate over time is, and the time aspect is really important. So that is where we will put, for today's pizza session, we'll put the focus on. But then you also have a last question. I just mentioned this because I like to mention it. The last question that you can ask, which is not in the scope of this demo, is when does the equipment start showing a different behavior? That's not survival analysis, that's anomaly detection. Because the different behavior is anomaly, and you have to build different types of models for that. But for today, we will focus on the survival analysis, so about predicting the probability of failure over time. I don't think it, yeah. All right, so we're going to delve now a bit into the theory of survival analysis. I like this picture a lot because this picture actually tells us already a lot about survival analysis. So imagine wildebeest crossing over a river. When they are at the one side of the river bank, they are safe because they are on land. And they try to cross the river, and there are alligators that try to capture their prey, the wildebeest. So if you build a survival function around this, you can frame it really easily. So if the wildebeest gets closer to the other side of the bank, his probability of survival will increase. So his probability of survival can be quite low when it's at the start of the one side of the bank, and it increases when it goes to the other side of the bank. And there are features in this situation that will add to that survival rate of that wildebeest. For example, its location. If it's in the middle of the herd, the probability of it surviving will be larger than when it's on the edge of the herd that crosses over. So these are typical features that contribute to that survival rate. If it's a small animal and a weak animal, it will have a higher probability of dying. So this is the typical survival rate, building a model with wildebeest as an example to try to cross the river. We will not use animals in this case, but we will
animals were hurt in this.
No animals were hurt.
Making this model.
That's a typical question or framework around survival analysis. All right, so we will learn about, but there are a lot of elements that come into play when you build a model. So you have to deal with sensor data. The example that I gave you, when you buy a second-hand car, you don't know what the history of that engine has been. So the data that you have around that engine is to some extent censored. And you can have different types of sensor data. So we will mention a little bit about sensor data. We will learn about survival quantities, about Kaplan-Meier estimate, which is a technique to build that probability curve over time, and the survival regression as well. And lastly, we will go over to evaluation techniques. So building the model is one thing, but evaluating the performance of the model is another thing. So, sensor data. As it is with life, well, I turned 31 yesterday, so I know that I will, in my life, I have turned 31, but I don't know what my future will look like. So it would be cool that if I could predict my survival probability over time to get an expectation of how long I will live.
Yeah.
So, but the challenge is that a lot of data is censored. I don't know how my future will look like. I don't know how an engine's future will look like. So, what kinds of sensors can I have? I mean, because we're humans and we are limited to time, and in physics, time goes only in one direction. I know that my future is censored. I don't know whether my past is censored, unless I had a brain injury and I forgot about my past. But with objects and engines, it's a little bit different. So you can have data of objects, or in this case, for example, engines or machinery, where you have something that's called left sensoring. It means of the historical data that you have, or not up until the point now, we don't know what its birth has been. So with the engine, you buy a second-hand car. That's called left sensoring. Then you have also called right sensoring, which is our case. As human beings, we don't know how our future looks like. And then you have something called the entire life cycle observed, which is actually ideal. That's in ideal situations what you would like to have. You know when the birth of an object or a machine, and the death of an object. But, yeah. So how does that look like in terms of data? So I give you an example over here, which is actually the data that we will use for our demo as well. We will work with rail switches, which is a machine that the rail operator activates whenever a train comes by, switches the rail depending on which trajectory that it has to go to. Well, you can imagine that with rail switches, there are only some rails that have experienced death to some extent. Some may not have experienced failure or death.
Yeah, yeah.
So if the data that we have, so let's say we have our observation of a specific type of switch, which had been operated at a specific time, which had these kinds of characteristics, well, we know that engine died. We know this one hasn't died, so the event is 0. So this is typical of the typical data that you have. If an event has occurred, it has a 1, which means we know that the failure has happened. If it's 0, it means censored, because then we get back to this image, which is right censoring, or maybe it can be both. But that we know that it hasn't failed up until now, but it doesn't mean that it will not fail in the future. So it can fail in the future. So that's the data that typical data that you would work with usually in survival analysis. Now comes the important piece, the survival quantities. So it is essentially, survival analysis is all about calculating the survival function. So how does my probability of failure look like after a certain amount of time? So we know at the birth, so imagine the x-axis being the birth and being the right axis here being the moment of now, and we have 10,000 machines or engines. We know at their birth, exactly at that moment, their probability of survival is 1, because everything lives. That's the birth. But over time, gradually over time, some equipments will fail. So you will know that for a specific machine, based on the collective
aggregated data.
Exactly. You know that, for example, there's a birth of the machine, and after 10 days, 30% of them died. So we can say of the rest of the machines, there's a 30% chance of them dying now.
So 70 survival.
Exactly.
Rate,
yeah. And that will, of course, decrease over time, that probability of survival. So that is essentially what we try to fit, because this image tells us already a lot. So imagine if we have a function that gives us this curve, some kind of analytical function of some kind of empirically approximated function. We can calculate exactly at this point what its or maybe at this point, what its probability of survival will be like. So at this point, its probability of survival is 50%.
Yeah. Question in the room.
Do you have to give it an expected distribution? So I think this is an exponential function.
We will get to that. It's a good question, but we will get to that.
By the way, do you guys see when Ismail points? Cool.
Yeah. All right. So if you have this function over here that gives you the probability over time, you can do a lot of things with it. You can also turn it around and you can calculate the lifetime distribution over time, which is nothing else of, it's 1 minus the survival rate over time, which gives you the probability that an event will happen before a certain amount of time. And that is how this graph then will look like.
It's the inverse of the other one.
Exactly. Yeah. And if you take the derivative of this function, it will give you the rate of deaths per unit time, which is actually quite logical for those who are familiar with calculating gradients and derivatives of functions. So, however, as you all know, a simple function like this, or even this, doesn't give us much information. What gives us more information is the gradient, so the changes that happen over time. Hence why the event density is a really interesting function, because it stores much more information. So usually that is what we, especially in a use case that is about survival analysis, that is what you want to figure out. When does most of the let's say the death of a machine happen? And if you have descriptive features of that machine, you can figure out which features contributed to that sudden increase in like mortality rate, let's say, over time. So, survival data is generally described and modeled in terms of two related functions. We have the survival function and we have the hazard function that I will get to in a minute. This is something that I would like you to keep in mind if I go over to the slides on the hazard function. The survival function represents the probability that an object survives from the time of origin to a specific time t. So it directly describes the survival experience of a group of objects, and usually is estimated by a specific type of estimator, which is called the Kaplan-Meier. And then there is the second type of model, which is the hazard function, which I will get to in a minute. So this is typically a model that we use to approximate that survival function of the data that we have. It's called the Kaplan-Meier estimator, and it's used a lot in the medical field, and I will give you an explanation in a minute. So what that does, it's a really simple function. It really is this function. So what it does, it just measures the fraction of subjects living over a period of time. So imagine in the start we have 10 subjects living or 10 machines living. Then that survival is 10 over 10, which is 1. So that we see over here. And at this time point t1, 8 of them survived, 2 of them died. So we get this point over here. And we do that over all the time points that we have in our data. So we get this curve over here, which is our survival function. To give a practical example, hence why it's always used in the medical field, imagine we have a new type of treatment for cancer patients. We have radiotherapy, and researchers have found, or chemists have found, a chemotherapy as well that you can use on top of the standard radiotherapy that the patient uses. So if you use that chemotherapy as well between two groups, one group that receives only the radiotherapy and the other group that receives the radiotherapy as well as the chemotherapy, you can see their probability of survival over time. And if you set this out against each other, you have a statistical proof that the chemotherapy will increase the survival rate of a cancer patient. So you can use this in all kinds of treatments in the medical field. And now we get to the second type of models, which are called the hazard models.
Before you go, can I ask a question? So does this always does this assume that the survival rate always goes down? And the reason I ask is I did an analysis for an insurance firm to look at what is the probability people will churn. And what we saw is that in the beginning the probability that they churn or their survival goes down, or the probability that they churn goes up. But then over time the probability just goes down rather than further up.
Okay, interesting.
So what we saw is if people are leaving, they are leaving quite early. If they are not leaving early, they're probably going to stay longer.
I'm looking at the equation, I would say that it would also capture that effect still. So
Interesting.
I haven't seen cases myself personally in where it goes up, but I think if you fit that estimator, I think it should then go up.
Okay, cool.
All right, then continuing about the second set of models used in survival analysis called hazard functions. This works a little bit differently. The hazard function gives the instantaneous potential of having an event at a time given the survival up to that time. So this probability that you see, so we have the hazard function lambda over time, and we have at the numerator the instantaneous potential of having an event at that time given, and that's the denominator, the survival up to that time. So it measures the rate of failure and provides more insight into the failure mechanism. And then we have something called the cumulative hazard function, which is an integral of that hazard function over time. So in contrast to survival function, the survival function only describes the absence of an event. However, the hazard function provides information of the occurrence of an event because it also uses this information about the rate, the potential of having that event at that time. But it's a little tricky to approximate this function because we don't always have that kind of information. Hence why there are a lot of analytical techniques used to approximate that hazard function, which we also go to in a minute.
And an event is death.
Event can be death,
Yeah. Okay.
or a failure of a mechanism.
Yeah.
So maybe to put it in another way, comparing a hazard function with survival function, I'm just going to rephrase what I just said, but maybe in a way that you will understand a bit better. The hazard function is the probability that an object that is under observation at a specific time has an event as well at that time. So it represents the instantaneous event rate for an object that has already survived at that time. And that is an important distinction to make with survival analysis.
So the likelihood or the probability that if you made it till now,
Exactly. Something
it's
will
going to happen today.
Yeah, exactly.
Or now. Yeah.
So looking at what I just showed you was the radiotherapy with the chemotherapy as well for that poor patients living. We also see here, for example, just to give you an impression of how a cumulative hazard function or a hazard function looks like, these are the graphs of how that looks like. And what you can also do with hazard function is calculate the 95% confidence interval of that function. Although a side note here is you don't see what the hazard function is of the other patient. But I just wanted to give an impression of how the functions look like. So you can indeed see already here that the hazard function looks quite differently than the survival function because it goes a little bit up in here. So how do we estimate that hazard function? An important thing that I would like to mention here, and that is the reason why usually hazard functions are used as well. The Kaplan-Meier estimates the early conditions of time. So it doesn't look at variates that influence that time, because in the equation, as you already saw, it just takes the event into consideration and the time of that event into consideration. It doesn't take features into that consideration. That is something that Cox regression, which is a method of approximating that hazard function, can do. And that gives us much more information. So when an event happens and we can fit a Cox regression that gives us that survival function rate over time, we can also use the insights on the features that contribute to that event happening. So not only can we tell this happened, we can also say this feature contributed to that event happening. And that is, for example, useful if you want to improve the quality of your rail switches. So if you have the different types of sensors or different qualitative descriptions of your sensors, you can then build this model to then do some kind of, let's say, similar to feature importance in machine learning, tell you what feature contributed to that rate. So if it's a sensor type, you can change that sensor type to another one, with maybe a better one that will be turned out in the model as well. So, with respect to your question, Jochen, the predicting that hazard function is quite difficult. So what Cox did is it used something called a proportional hazard function, which is a little bit based on empirical equations to approximate that. So this is how that equation looks like. So we have our hazard function x of t given some features, and then we have this equation. So we have something called the baseline hazard function, which we don't know, but studies have shown that you can estimate it non-parametrically. So hence why, when you build a hazard function, you can use non-parametrical features or coefficients to help build up this equation. So you don't exactly have to know the mechanism of that survival. You can approximate, estimate it non-parametrically. In this equation, our x are the covariates or the features, and the w that you see over here are the set of the unknown regression parameters, or the weights, if you're familiar with machine learning, that you have to know. So imagine that we have a data set with 10 features, 100 rows. Like with standard machine learning, when we fit a model, let's say a linear model, we want to find the right values for the weights, so the coefficients, that gives us the best probability estimate curve.
Yeah, so it's e to the power of the end product of your weights and your
Yeah.
features.
Yeah, and that non-parametrical lambda 0, the baseline hazard
Yeah.
function.
Times like a starting point. Yeah.
And if you look at this equation, I'm going to go back a few slides. The survival function then becomes the e to the power of this equation here. So based on the hazard model that the hazard function that we can approximate and fit over here, we can reconstruct the survival function, which is e to the power of that function.
E to the power of minus e to the power of the end product.
Yeah.
Times,
Yeah. So 2 times e to the power, that's correct.
Yeah.
So then the question is, how do we determine that weights?
Yeah.
I think it's a good question to ask to the audience here. Maybe to help you give the answer, how would you determine the weights of a linear regression model?
X-accent X min 1, X-accent I.
Yeah. So you would
Gradient
use,
descent.
exactly, you would use gradient descent and use a metric like mean squared error or mean absolute error, and build that into your gradient descent model to converge to a set of weights that then gives you the ideal fit. Exactly the same case here with Cox regression. However, we don't use mean squared error or mean absolute error. We use something that's called the Cox partial likelihood, which is quite a complex, may seem as quite a complex equation, which it is, honestly, also to explain to you. But
You can do it.
so what this does is, when we fit a survival function on data that is based on events, it's not about predicting whether a machine died at exactly day 450, let's say. So what this equation says is, it's all about predicting whether a machine will die before or after another machine. So what this equation does is it just tries to place the order of the machines failing in the right sequence. So what it does is it takes, so let's say in my data set I have 10 machines and they died after a certain point of time. It takes that one machine, and when we fit our Cox regression model, it plays around with the weights and then checks, did this machine, let's say machine 3, die before or after all the other machines, and it's going to place it in the right order. And then it takes the other machine and then check, did this machine die before or after all the other machines. And then it converges to a sequence where the order of the machines dying is in the correct order as what the data tells us. And that then becomes the weight, the set of weights of our Cox regression model. Because we have that time data, so it's not really important telling day 450. It's all about figuring out whether it dies before or after.
And it's just the order. It's not
it's
the
the
time
order.
between.
Yeah, it's the order that it tries to figure out. Hence why we have, to be honest, I forgot what this was called in Latin, the capital P, but hence
Pi,
we,
yeah.
oh, it's the same. I'm not good at
It's the
Latin.
product.
Okay. Hence why in this equation we have the product of all the time to events time E, or event at time E product, because you take the pair of that machine and set it out against all the other machines. So there are also other methods besides Cox regression, because as I already mentioned, Cox regression uses that baseline hazard function semi-parametrically, so it's categorized as a semi-parametric model. We also have other parametric models like the log logistics, the Weibull, and the exponential function, or even non-parametric models.
And those they just take an assumption that it
Exactly.
looks like this.
Yeah. So the Weibull regression provides estimates of baseline hazard function, but because of technical difficulties, it is seldom used in medical literature. The hazard function has to be monotonic if there is a peak. For example, when the course of a disease reaches a mortality peak after a certain amount of time, it won't converge, hence why it's not really used that often.
And with the Cox regression, you can deal
exactly,
with that.
yeah. And the Allen's additive model works quite well with sensor data, so keep that in mind. So in the future, if you have to work with data where you have a lot of sensor data, you can use the Cox regression model, but looking at literature, the Allen's additive model is actually also a quite good one to use as well.
Cool.
So that's just an idea to place the Cox regression model with respect to all the other models. So then we get to model evaluation. I actually already gave you the model evaluation, which is the Cox likelihood regression. But that one uses something called the metric. Like with linear regression, you have the mean squared error or the mean absolute error, and then you use the gradient descent to find the optimum set of weights. In the Cox regression model, getting back to that equation, it uses this partial likelihood equation, which it then tries to minimize. But it uses the concordance index as a metric to minimize that the Cox likelihood regression, and I will get that to in a minute. And then we have also something called the Breyer's score. So I won't get into this. I think I'm a little over time as well. That's not that important, though it's standard model validation. All right, so the concordance index. As I already told you, concordance index, this is just a graph that helps you understand actually the story that I just told you about trying to fit the order of an event with respect to all the other orders. This is the index that we will use as well in the demo. And the package that we will use for the Cox regression model already has this concordance index in it, so we don't have to program it ourselves. But this is just basically telling that story that it is all about trying to place that event with respect in the right sequence or order with respect to all the other events. And maybe important to mention here as well, the concordance of a random model is based on how this equation here is constructed is 0.5. So if you're going to build a model and you're going to fit it and want to assess its performance, it has to be higher than 0.5 and it converges to 1. So if it's 1, it's a really good model. If it's close to 0.5, then you know it's not that good of a model. Then we have also something called the Breyer score. What do you notice looking at this graph with respect to this graph?
The bottom right graph.
That too. But what this graph doesn't tell you is the performance, aka the concordance index, over time. That is what the Breyer score does do. Yeah. So it gives you the performance of a model, and the x-axis here is time. So it gives you the performance of your model over time as well, which gives a lot of information about the performance of your, because you will see that in the demo as well. You can have a model that is, let's say, 0.65. It's not that far off from 0.5. But if you use the Breyer score to evaluate the performance of that model over time, there will be regions in where the model will perform better than other regions. The explanation is quite simple as to why, but I'm not going to tell that now. I'm going to tell you at the end of the demo.
It's the cliffhanger.
Yeah. And I won't get too much into the mathematics of the Breyer score, but essentially that's what the Breyer's score does. So that's the theory, and from here on we will go to the hands-on session.
All right. So thanks, Ismail.
Yeah.
Very intriguing. Very intriguing.
Sorry, but maybe before I hand it over to you, let me tell you a little bit about the hands-on session, which I forgot. So we will work, as I mentioned, on this switch data. So we have different types of switches, and what we're going to do in this demo is we're going to calculate or predict what the probability failure over time will be like. And I gave you an impression of how that data looks like. So we will fit a model, a Kaplan-Meier model, and a Cox regression model, and then use the validation technique to validate and assess the performance of that model.
Perfect.
Yeah.
Cool. So what we are going to do is we are going to play the demo. We pre-recorded that because we're going to have way more fun in the office going through the demo here. But we don't want to bother you with us eating pizza. So we're going to play the demo, leave it running. Thanks for watching. This is the last one of this year. There will be more to come next year, where we will be streaming new events and new hot topics. Think about generative AI, think about reinforcement learning, think about lots of NLP on the list, natural language processing. So stay tuned, we'll be back and have fun with the demo. Thanks.
Hello, everyone. So this demo will be about how to put the theory on survival analysis into practice. And to do that, I have prepared this Jupyter notebook where we will work with data on the rail switches that gives us an overview description of the various rail switches, its operational data, and we try to predict a survival function on the rail switches based on the data and try to infer what features are an important indication to the lifespan of those rail switches. So basically, the theory that we discussed during the pizza session, we will put that into practice in here. So to be more specific, we have data on rail switches combined with the weather data. We have a data set containing information on 120 machines. And whenever a switch gets activated, the data records the turning time of a switch, the angle of a switch, and the load, the electrical current that goes through the switch during operation. Let me show you an example of how that looks like first. So we read in the packages. This is the most important package that we need. It's like the scikit-learn for machine learning, but for survival analysis. So all the tools and packages that we will use them from this package. So let me show you how the data looks like. So this is the data that we have. So we have a switch ID, the location of a switch, the direction, whether it's a left or right. We have the switch type, because a switch can have various types. The turning time it took to make that switch, the angle of the switch, the date time of when that operation, when the switch got called, let's say, happened, and the weather data together with information on whether it's filled, yes or no. So really important here is that we need to do some data pre-processing to get some descriptive features around let's say, the average turning time per switch. Important thing that we don't show here, as you can see here, because I dropped it, and that is to do with because it doesn't fit into the data frames rows, is the time series, which is let me show you here, is this is Pandas time series. Because we read the data frame from a CSV, it doesn't recognize the data in its proper order. So if we print the V types over here, you can see that everything got recognized correctly except for two features, which are the date time, which is an object, and the time series, which is the load data, which is a Python list. However, because we read it from a CSV, it reads that Python list as a string. So we need to correct for it. We need to convert this string back into proper Python list, and that is what we do here. So I built this function, clean time series. So I call it in here. So when that is finished, I'm going to rerun the cell, and you will see that this time it's a proper Python list. And I'm going to delete it. And if I show you, let's say for the 500 operations, how that looks like, you can see how the load looks like over the duration of when the electrical current was going to the switch. Interesting is that you can see quite clear different lines, graphs actually. So there's a lot of indicative power in this loads that go through the switches, and we can use them as feature as well. So getting back here, I didn't put that in here because let me show you if I do put that in here. It's a Python list, so it's gonna blow up every row. It's not nice. Okay. Also, the pandas, the date time has to be a proper pandas date time, which we do over here. So once we have done that, then we have the data in the right shape, and then we can start to feature engineering. So again, I just mentioned we want to build indicative features like descriptive features on the switch types. So I have listed the transformations that we're going to do. First off, and we're going to use this as features, indicative features, to build our survival function. So first off, we're going to calculate how many times each switch is used per year. We're going to calculate the mean statistics on the turning time, temperature, and load. And also, really important is we need to get the dates of the first failure happened. We need to get information on whether there's sensoring. We need to get information on the day of first measure of each switch, because these are important. The day of first failure and the day of first measure are the tables that we use, and I'm gonna back here, to calculate whether a machine, whether it has ever failed, yes or no, and two scenarios. When it had failed, we're gonna calculate the column T. The E stands for an event. Did a failure happened, yes or no? And the T stands for time. So two scenarios. When a failure has occurred, the column T, which we still have to create, that is that feature engineering, the data pre-processing, gives the amount of days between the first use of the machine and its failure. When it hasn't occurred, the time will give the amount of days between the first use of the tool and the last time information of the machine was logged, which is actually quite logical. Okay, so let's start with the pre-processing, feature engineering. First off, we're going to calculate the number of yearly operations. Well, pandas date time is a combination of date and time. We're not interested in time, so we can only extract the date. And really important is we're going to sort the data frame on that date, and I will get to that reason why we do this. So keep this in mind. We sort the data frame based on date from low to high. Okay, now we're going to calculate the number of yearly operations, which is straightforward. We group the data frame by the ID of the switch and the date. Let me show you actually what this does. This one as well. So this tells us for ID switch 0, there was one operation at this date, one operation at this date, two operations in this date, but we want to get the overall size of this. So how many operations in total happened for ID switch 0? We use that by, again, we regroup by ID switch, and then we're going to calculate the sum. So this tells ID switch has in total called 990 times. We divide that here by 3, and then we get the data frame usage, which says for ID switch 0, it had 330 times an operation. Subsequently, we're going to calculate the mean turning time and temperature per switch ID and mean load. And the way how we do that is, first off, the problem with the time series is for every operation that happens, so for every time a switch had been called, it gives us this time series data. And we're going to calculate the mean, which is actually quite straightforward, like this. Okay, not like that. NumPy times mean. Like this. Okay, so we have the mean. But this is for every time a switch had been called. So let's first do that. We do that way simpler like this with the apply function in here. And then we're gonna group, we take the data frame of, these are the 3 columns that we are interested in, the turning time, temperature, mean load, because these are the, we're gonna calculate the mean for these. This mean load refers to the mean load per operation, but we want to get the mean load per switch ID. So if a switch if a switch has been called 100 times, for every one of those 100 times, we're going to calculate the mean load, and then we're going to calculate the mean load for all the 100 times. So that's basically what we do over here. So we group by switch ID of the mean load, temperature, turning time, and then calculate the mean. So we get this one. So for every switch ID, we get the mean turning time, the mean temperature, and the mean load of each mean load. I know it sounds confusing, but that's what it is. Okay, now we're going to calculate the we're going to calculate the first failure per switch. So if a failure happened, when did that happen? The first failure. So we take the data frame, we filter based on whether a failure happened. We're interested in the ID switch and date. We group by ID switch. Let me reconstruct this as well. Okay. So this is, let me fit them all in the same row. This is what we get. Okay. Now, if I say first, remember what we did here. We sorted the data frame by date based from low date to high date. So if I say take the first, which does this, refers to take the first record of that grouped function, of that grouped table. So it will take the first date, and remember, in the background, it had been sorted from low to high. It will take the first date of when a failure happened. If on the contrary, if I say last, it will take the last date of when a failure happened. But we are interested in the first failure that happened. So that's what we do over here. And then we get this. Okay, now we're going to calculate the switches that never failed. So how do we do that? First, with the set function of pandas, we're going to look at all the switches that we have. So these are all the switch IDs that we have, which are all switches. Then we're going to filter the switches where a fail happened, which is this one, and create that set. These are all the IDs of the switches where a fail happened. And with now this is a set, this is a set. The cool thing of Python with set is if I say set take A and B, I'm going to calculate and I'm going to subtract this one with this one to get the leftovers of the switches where a fail didn't happen. You can do that really easily with symmetrical difference. So if I say take the symmetrical difference between, this also has to be a set because I can only do it with sets. Take the symmetrical difference between these two, I get over with A. The reason why it's called symmetrical difference, if I remove this A from the left side and put it at the right side, it still gives me that difference. So I add here, and that's what I do here. I add here the ID of all the switches. I add here the ID of the switch that failed. So if I calculate symmetric difference, I get left with the ID of the switch that didn't fail, which is interestingly 0. Okay, which means that we don't have censoring data. So if I just print this, it gives me empty. Now, I'm going to concatenate those two. It kind of gives me the same data frame, but that is what it is with the data that we have. Okay, now we want to get the day of the first measure of a switch. So when was the first time something on that switch was recorded? So we do that by this one. Again, we take the date, the ID of the switch, we group by the ID of the switch, and we take the first. Set is it's similar as to what we did with the this censoring and with the first failure where we took the first. But this one was filtered on when a failure happened. This doesn't do that. This just takes the first of all the data for every switch, grouped by every ID switch. So this then gives us the data first record that happened for every ID of the switch, every switch ID. Now we're going to construct that final data frame for survival analysis where we bring all these information together. So this is important. I take the data frame of the ID of the switch, the location, switch type, angle, and I'm gonna drop duplicates. But remember, the data frame was sorted based on date from low to high. So if I say take the drop duplicate, it's going to delete everything except the last record that it made for that switch. And then I'm going to merge that with the data frames I created here for every switch ID. And I do that using pandas reduce. So what pandas reduce does is it applies this function merge to this one with that one. So it creates a new object, which is a merged between these two. And it's going to merge that one with this one. And then the same, it's going to merge that combined with this one and then with this one, so that we get this overview. So we get the ID of the switch. And these are the things that we had calculated. So date first, date event, turning time, temperature, mean load, and number of yearly operations. So the only thing that drop duplicate did is it dropped the duplicates on this one, but they are always the same. So yeah, so we just remove it because it's drop duplicate. So let me show. If I take this, it's gonna show me this. Yeah, and if I drop duplicates, now I have 100,000 rows. That we've got duplicates. Every switch has a specific location which is fixed, right? One switch cannot be at two different locations. It cannot have two different types, and it cannot have two different angles. So just left with this. Okay, and then I'm gonna add these descriptive features for each of the switch, which are all, these are all aggregates, and these are the data first record and date of first event. Now we're going to create the survival specific columns. So we had to calculate T, which was time to event. So the way how we do that is we take the date of an event, subtract that by the date a first record happened. I don't care whether that event was a failure or not failure, but it's an event, subtract that with the date of first thing happened, and I create this T. This is time to event. It's already pre-printed, sorry for that. Now for E, the interesting of NumPy where function is that you put in a condition, which is this one, and then it returns 0 if that condition is true, it returns a 1 if that condition is false. So we're going to take the ID of the switches for data survival, and then we're going to say, are the switcher IDs that were censored in this series? Yes or no? Well, this was empty. So which means it didn't happen. So it will assign a 1 because it will assign a 0 for when the condition fulfills, and it assigns a 1 when the condition doesn't fulfill. And because we have 0 censorings, it will assign a 1 for every one of them. So now we're going to let me run this one. I'm going to drop these two columns because, yeah, we only needed that to calculate T and E, so I dropped them. And then problem switch type is a number, and I want to apply one-hot encoding, so I need to convert that to a string, which I do over here. So add the suffix T to these, so then I can apply proper one-hot encoding to it. And then, as you can see, we only have events where a failure did happen. So we don't have any censored data at all. So we're going to create one for the sake of this demo. And we do that over here. So we say, okay, we want to have 20 censored data. And we're going to create the random the location for that censored data randomly. So we do a random sample, and we take the values from the location and then create a censored location. And we do that for all these features over here. We're going to construct the data frame for the survivor censored over here. So this is what we get. Again, all the events are 0, but nothing happened because it's censored, right? So it all performs a repeat. So we get this censored data. And then we concatenate the observed data where there was no censor at all with censored data. And then we get our data frame survival final. We're going to apply one-hot encoding for the categorical columns over here. And we're going to rename them and call them data frame. And that is the one that we will use from now on. Okay. Now, data exploration. So first off, we want to get an insight of the sensor data with the observed data. Lifelines, again, the package that we use as a really cool function called plot lifelines. We assign the variable t as the time column, this time to event, and e is the event itself. These two are really important because we will use these variables when the code blocks below. We take 50 random samples to make it containable in here, and we're going to plot it. So the red lines and dots are the switches for where an event occurred, and the blue ones are indicate censored observation. Interestingly, looking at this, you can see that already the censored data has a much lower, the observed data has a bit lower time span than the censored data because they generally tend to live longer. Let's show that in a distribution. So we can see that if we calculate that distribution, we see that indeed the observed data is more concentrated in time between around 350 and 450. You can see that in here for observation 1, where an event did happen. I mean, the first and third quantile is between 325 and 400, while for the observed one, it's between 200 and almost 1200. So this is a bit more spread. So this will create bias. So keep that in mind. We will see the effects of this also back below. Okay, so keep in mind, using this information, we have to be careful when making a survival regression model. Okay, now we're going to fit the Kaplan-Meier estimator. So we use the lifeline package import Kaplan-Meier fitter, like when in SciPy we import random forest or whatever. We define a timeline with steps of points for which we want in where we want to calculate the survival function curve. And then we define our fitter, the Kaplan-Meier fitter, with a 95% accuracy interval. And then we're going to fit it. So we fit it with the time of the data frame. So this is the time column. And we say this is our events that we observed. That is this column. And we want to calculate it over this timeline. And when we run it, we fitted it. First off, let's print what is the median survival. So it says the median survival time is 354 days. Now, if we plot that function, this is what we get. This is the survival function for the Kaplan-Meier estimate fitted on all the ID switches. So this gives us an overview of the survival duration over time for all the switch IDs. So let's say we are interested. So what we can do with the survival curve is we can also calculate what the probability of survival is at a certain time. So we say, okay, we're interested in 256 days. What is the probability of survival at t 256? So we can take that survival function using this one. And then we're going to calculate the probability of a survival up until 256 days by this line block. And then we're going to use that t and p and overlay that with the exact same plot that we made over here, which is this block. However, we're going to add this vertical and horizontal lines in here. So this says that the probability that the time of death is later than 256 days is 0.91. So there's a 91% chance that the switch will stay alive at 256 days. So that's what we can do with the Kaplan-Meier survival. But this is we fitted this survival function for all the ID switches. If we want to show it for, let's say, 2 switch types, so we take the switch types on which the most number of operations happened to make it more reliable. So we take these two that we do over here. It's not interesting how we get it, but important, these two is the one that we take. And we're going to refit the Kaplan-Meier fitter on those 2 switch types. This is what we then get. So we can see that a switch type T1 has between 4 up until 800, roughly 750. Switch type T1 has a higher survival rate with respect to switch type T0, but it has a longer lifespan than switch type T0. So this is kind of the information and insights that you can get out of this using Kaplan-Meier fit. Okay, now the problem with with Kaplan-Meier is that it only conditions on time. So you cannot condition the survival function on covariate, and which also means that you don't know what covariate causes a death or an event to happen. You can get that kind of information using Cox regression. But before we do that, we're going to explore the features we're going to use. So we say, okay, these are the numerical features that we are interested in. These are the Boolean values. That's from the one-hot encoding. So my features are the Boolean plus the numerics. And so we get this overview. And let's plot the distribution of the features between the observed and censored events. So how does the feature distribution look like for the switches where there was an event that did happen and an event of which a sensor in which a switch in where event is censored. So this shows for every feature: angle, temperature, turning time, etc. It shows the feature distribution for angle for a switch where an event happened in orange and for censored event in blue. It's important that these distributions are quite similar. If they are not similar, which means symmetric, there is a risk of covariate dependent censorship, but we won't deal with that in this demo because we don't have the time, it will take too long. So, but what this doesn't show us is how it looks over time. So if we create a scatter plot where we calculate the values of the features over time, this is what we get. And we see that there is no correlation with time, which is good because that's what should happen. And this is then the correlation matrix. Interestingly, you can see that there's a higher correlation between turning time and mean load of this switch, which actually seems quite logical. And there is no high correlation with time for any of the features, which is good. Okay. Now Cox regression. Again, we're gonna use the Cox regression instead of the Kaplan-Meier to condition on covariates as well. We're gonna use the Lifeline packages for that, but the problem with the Lifeline package is that it's quite really different from sklearn. So we're gonna build wrapper functions where we wrap the function, the functions from Lifelines and wrap that around an SK and scikit-learn framework. So it's not interested what happens here because this is the wrapper function that I built. And what this does is it transforms that package into the same operation style as scikit-learn. Like, for example, with scikit, you say fit and then predict and then transform, etc. Like these kinds of operations, we can do them with this wrapper as well. We're going to use the concordance index to get a sense of the performance of the model. Remember, concordance index is all about predicting whether the expected lifetimes of an observation happened with respect to another observation. So it says, okay, if a switch dies at time 400, it's not important that the Cox regressor can predict as accurately as possible that the machine or the switch died at exactly day 400. It's all about predicting whether that machine indeed died before or after another event. Hence why it's called concordance, because it calculates the concordance of that event of a switch with respect to all other switches. So it has to be higher than 0.5, which is then good. So we generate that function concordance index that does this over here. So we calculate that concordance value. Actually, when I wrote this function, I realized it's a bit redundant because Lifelines has an update, had an update, and it can do it itself now. Okay, now we just generate our concordance scorer, which is still a function, so we haven't done anything with it yet. And we wrap that concordance index also in an sklearn compatible wrapper using the make scorer function of sklearn metrics. So we take the concordance index from here, which is actually quite similar to this, really, and then wrap it here. Okay. When we fit the Cox fitter model, it is quite difficult to get convergence. So I did achieve convergence playing around with this hyperparameter penalizer. I won't get too much into details. I will send you a copy of these notebooks as well, so you can just go through them a bit longer in your own time, and also read on the documentation and how you can improve the stability of the feature, etc. Okay, so for me it worked. So I import the Cox filter, I define it over here. Again, 95% accuracy. This is the parameter I set with which I got achieved convergence. Also important is I started with an initial points that I created to help improve that achieving convergence. This is similar to, when you fit a model at sklearn, it starts with a random initial set of weights, and then it's going to converge to the proper set of weights. Something similar to that is the initial points. So we built our estimator using the wrapper, the sklearn wrapper. This build estimator is this function over here that builds a pipeline around the Cox filter using these wrapper functions. But that's not important, and I don't want you to get distracted there. So we have our estimator. Before I'm going to fit it, I'm going to save it as another parameter because I will use it later on. So I run this as well, and then I'm going to fit it. So I say this is the data that I have. So I take my data frame. These are my features. This is my, and let me remove this because I can understand that this may confuse. Let me remove this as well. Let's put it here. Let's remove it altogether. Okay, so this is my X data frame with these features. My I is my data frame with my time column and event column, because Cox regressor need the time and the event as your response values to your data frame. We're going to fit it here in sklearn fashion, hence why this is the reason why we even built that wrapper function to make it like this. And then we extract the fitted fitter from here, from that wrapper function. And cool thing is, because we have extracted it, we can use the inbuilt plot function of lifelines, the Cox P8 feature, to give us an overview. So I'm going to train it here, and it's finished, and it plots me the results and the statistics. So it says these are the coefficients for my features. So this tells me these features. So now I have fitted a survival curve based on these covariates. And interestingly, these are just exponents of the coefficients, but I'm always interested in the coefficients and the p-value, but you can show them here as well. That's funny. Let me rerun it. I think there's a random element in here. Okay, there isn't. Okay, actually there is, but I won't get to that. So now it shows us which features are important to build that, to get that accurate survival curve. So it says that, look, this feature was important, that feature was important, and that feature was important, etc. So this now gives me an overview. Also, it tells me which features contribute to an event happening. So when a failure happens, yes or no. So apparently switches in location E have a higher probability of failing than with respect to other locations. So these are the types of insights that you can get with Cox regression as well. So let's look at the subset of switches, because this has been fitted on all switches. So if we just select 6 random switches over here and we plot their survival curve, this is then what we get for every individual switch. And so that's why we have only assessed our fit on the whole data set. So if we do a cross-validation to get a more accurate and representative predictive performance of a model, this is what we do over here. So we generate initialize our cross-validation method, and then we use the cross-validation score of sklearn. We put our Cox regression in it, our X and I, the times of cross-validation that we want to perform. And then our scoring, we define our scoring as the concordance scorer. And then it gives us a 5-fold cross-validation overview of the performance of our model. It's a little bit higher than 0.5, which is good for some of the splits. There's one split where it didn't perform well at all. Something weird is happening here, which I still need to investigate. So this is then an overview of the performance of the model. So you can play around with, if I go here, with the penalizer. So let's change that to 0.2 and see what that does. Similar values. Okay. So that is the how we fit the Cook's regression model. And also interesting is the prediction error curves. The problem with the concordance index is that it doesn't show the performance of the model over time. You can do that with the weighted Breyer curve. So if we want that predicted error curve over time, then we can use this method. So, and we can also use the Breyer score to compare like Kaplan-Meier against Cox. Okay, so we define our X train and X test. We split our X and I over here. We define our Kaplan-Meier fitter and we fit our data. We fit the Cox regressor on our train data. And then we do predictions on the test set. And let's run that. And then we're going to overlay that plot with the coin flip of the Breyer and the Kaplan-Meier and the IBS and the Cox regressor. So what this shows over time, that the regression model performs better than the Kaplan-Meier model, but also that especially in time between 350 and 800, that the regression model fits better than the coin flip, so the random guessing. So why is that? Actually, interestingly, the reason why that is it has to do with this distribution over here. Let me scroll up this one. Because the observed data that we had of when an event happened was exactly between 300 and around 400, the first and third quantile. And the censored was quite large space. So because we had data, especially around this region, our model is quite well in predicting whether an event happened in that same time period, hence why it is better than random guessing in that same time period. But outside of it, where we didn't observe an event, it's not that good. So the cool thing about using this prediction error curves is that you can also assess the performance of your model over time. And this also shows how reflective the performance of your model is with the data that you have. So that was the demo. Again, there's some extras over here that you can do. And I also play around with it. I will send a copy for you to